Hello and welcome to Toddcast 54. My name is Todd Bennett, and I'm going to kind of do a reintroduction of what these are because there's a high probability that there'll be some people coming in and just starting the sequence, this series right about now, because this is some of the stuff that's more tested on standardized exams. So again, these videos, they're aimed at two audiences, and I'm probably hitting 80% for each, not doing it perfect for each. But if you were taking second quarter organic chemistry, alcohols, carbonyls become a major part of that material. If you're taking first semester organic chemistry, most classes will have this topic end up being the last 2, maybe 3 weeks this semester. Some courses, it might be the start of second semester. But the point is, it's a pretty hefty and critical topic. It carries over to a lot of bioexamples. It is core to a large amount of organic chemistry. And so consequently, it's one of those things that's in every course and every standardized test that has chemistry in it, organic chemistry in it at least. And so it's important to review this. And so I'm going to kind of have even a change of tone from the previous 53 podcasts, and that want to just make sure we look at the big picture, how to apply it, both in an organic chemistry class and then the things you need to memorize and how it applies to other fields. So the tone change is going to be significant, and the audience I'm considering is going to be larger than just people taking an organic chemistry class. So with that in mind, this one is about the introduction to alcohols and alcohol reactions. And you get some of that when you do SN2 and SN1 reactions to make the OH a better leaving group. You sometimes do things to it, such as tosylate it, mesylate it, convert it to a bromine or chlorine. So you do encounter some alcohol reactions outside of this, but we're going to kind of treat everything as first contact. Okay, so important to know what an alcohol is. And alcohol just basically is an OH group on an sp3 hybridized carbon. And so I not only want to point out what it is, but sometimes what it isn't, what we mistake it for being. So an alcohol, in this case, on an sp3 carbon, you can have an alcohol on an sp2 carbon. It's called an enol as opposed to an alcohol. And so that is doable, or sp2 is part of a carboxylic acid. But a pure alcohol, in the sense, is on an sp3, such as this. Ethanol, one of the most common examples. Glycerol, very important in biology. Fatty acid triglycerides have three esters that have been added in place of the OH. Phospholipid bilayer is made up of one of these groups turning into something in the nature of a phosphate or a substrate of phosphate or some group, depending on what type of lipid it is. And then two carboxylic acids adding on here to form ester chains as well. So fairly important alcohol. Isopropanol, just a common household antibacterial. So it's, I don't know, you put rubbing alcohol in something at some point in your life. This is the main component, the active ingredient in rubbing alcohol. Albuterol, used in inhalers for asthmatic response, suppresses the asthmatic response. I want to point out in this one, so for this, it's clear what the OH is. There's three OHs. There's no OH here. But in this case, here's an OH on an sp3. Here's an OH on an sp3. But this is on the benzene ring. So I want to emphasize, although it falls into the overall class of an alcohol, an OH group on something, well, namely a carbon, this is going to be overall called a phenol. We'll get into that example soon. And then cholesterol, you have an OH over here, lots of other molecule part, but this one OH here means cholesterol, ending in OL, is an alcohol. So alcohol nomenclature-wise, end in ol, whether it's the common name or the IUPAC name. Ethanol is an IUPAC name. It's actually fairly common as well. Everything else, glycerol, isopropanol, butyrol, and cholesterol, are common names. Okay, so the OH makes an alcohol. The three OHs, still an alcohol. It's a triol. We have three ols, still an alcohol. This OH makes that an alcohol. These two, I'm sorry, these two here and here make an alcohol. This is a phenol again. So I'm going to put them in gold. Just emphasize that although it's an OH, this is known as phenol. We'll look at that in just a second. And finally, cholesterol as the OH there. So fairly straightforward. Those are some common alcohols or some reoccurring alcohols in both organic chemistry and biology. Common phenols, salicylic acid, aspirin, has a carboxylic acid functional group, but it also has a benzene ring with an OH, making that a phenol. Capsaicin, the really hot spice that we try to get rid of. And so here's a fun fact for you. When you look at this molecule, if you're going to think from an organic standpoint, um, whether it's polar or nonpolar, you got a couple polar groups, but um, overall, this long chain here in this part makes it more on the nonpolar side. So if you take a bite of pepper and it's burning up your mouth, water really doesn't help because water won't dissolve it and rinse it away. Has to have something with a little more lipid in it. That's why a lot of times they say if you drink milk, it'll help take the spice away because milk has enough lipid and enough water in it both to help this amphipathic molecule into that solvent. You swallow it and takes it away from your taste buds. So it's still spicy elsewhere, but you're not recognizing because it's not hitting your taste buds. Epinephrine, um, adrenaline, that's in our own natural cycle of, well, fight or flight is the first thought that comes to my head. But this is a phenol, but actually you'll notice it has a benzene ring with two OHs. We actually call that a catechol. So catechol is a special case of phenols. And we have an amine group here. So this is what's known as a catechol amine. You may learn about that as a neurotransmitter if you take a bio class or a psychobio class. And then tetrahydrocannabinol. So this is just common and hallucinogenic. It is an alcohol OH group on a benzene ring, so phenol right there. So let's just look at the phenols. There's my phenol and salicylic acid, aspirin. Here it is in capsaicin. This, again, is actually a catechol, which is just nothing more than a special case of a phenol with two. And then finally, on this last one, you have your phenol system there. Okay, so you can recognize the functional group. That's important. Properties of alcohol, depending on how long the chain is, they're relatively water soluble or miscible. They're liquid. And most alcohols are liquid, so I should make that a point. So miscibility or solubility, they exhibit hydrogen bonding, which allows that to occur. Their boiling points are actually relatively high compared to compounds of similar mass. So let's consider propane, 3 carbons, 8 hydrogens, so 36 plus 8, around 44 for molecular weight. Negative 42 boiling point. Propane exists as a gas at room temperature. We typically have to compress it. If you compress it under high enough pressure, you can force it into being in a liquid state. Hence, propane tanks are filled with pressurized propane gas, which will eventually take on, after enough pressure, a liquid state. Fluoroethane, chlorofluorocarbons were common as a refrigerant for many years, so this is on the low end of the scale, also around 48. Notice the boiling point a little bit higher because of the polarity, but not much. And then you have ethanol, massively large boiling point compared to the other two, despite being comparable in molecular weight. So molecular weight and intermolecular forces both impact boiling point. So if you're around 44 to 48, apparently your boiling point should be around negative 40 because of the H bonding, much higher. Okay, methanol, relatively high boiling, or well, higher boiling point than things of equal mass in the 56 range. Highly water soluble. It's basically water with this methyl instead of an H. And butanol, a little bit longer chain, so it's semi-miscible in water, semi-soluble, and then octanol starts to become insoluble. So once your chain gets to around 5 or more, the solubility drops drastically. So ethanol, highly water soluble, methanol, highly water soluble, propanol, fairly water soluble, butanol starts to diminish until finally propanol and higher. We typically consider those to be insoluble. Okay, so hydrophobic N is very small, so it's going to dominate and be mostly water soluble. Your hydrophobic and your hydrophilic are comparable. So this one is going to be kind of a little of both. And then for the last one, your hydrophobic is massive. Your hydrophilic is tiny, so that this N dominates the solubility. So water soluble, because this is So important, and this is so tiny. A little bit of both, and then this one, lipid soluble. So miscible in water, immiscible in water, and semi-miscible or partially miscible in water. Okay, so we have some properties. I'm assuming most of you actually ran into those same properties when you did some sort of OChem lab experiment on them. The acidity of alcohol. So keep in mind the 5 to 10, 15, 20, 25 rule. So for common organic compounds, carboxylic acids, around 5. In reality, they're down to around 2 to 5. 5 to 10, I say it 3 times. Phenols, thiols, and protonated amines are around 10 for pKs. Alcohols are around 15, maybe a little bit higher. Alpha protons, so that H right there is around 20. And then 25, that H right here is around 26 actually, but I'm going to say around 25. Just if I memorize this. So the pKs, do not, and again, I want to emphasize this, something I emphasized in the previous podcast when we got into pKs, and I want to repeat. Every textbook has slightly different values, mine included. So at this point, written an MCAT textbook or organic chemistry for the MCAT textbook, and also have written a just organic chemistry review book. In both of those, I have pK values, and they are collected by taking the average value I could find from any resource available to me. Textbook, online information. If I did a lab experiment, I'll toss that in there, any resource whatsoever, and did an average value and used that for my pKs, and was very, very surprised that my pK values in my books, they don't even match, one book doesn't even match the other book, which is kind of crazy. But that's because more information was gathered for one than the other. But the point of this being, no two textbooks, no two research papers, no two professors in class, no two review books, no two anything will have quite the same values. So know them in general. You know them in general, you'll be in good shape. So 5 to 10, 15, 20, 25 for your common organic compounds. So for us, that's where this comes from. And then when we get to phenols, note that they're around 10. Okay, so you clear this. Phenols, pK around 10, ethanol around 15, T-butanol, because of the bulkiness of these groups right here, they block the ability for this to come in and interact with another molecule, and weakening that H can't come off as easily because another molecule can't close enough. So pK drifts up, and that's why it ends up a little bit higher than 15. Cyclohexanol, same sort of story. It's really hard to get into a cyclohexanol in that chair conformation, so it ends up being a little bit higher. So just random point of interest. I'm going to toss one other thing out here and say that for those of you going on to biology, you're going to have to memorize the pK for the side chain of various amino acids. So every amino acid is going to have that background. But if I have a CH2SH, that's a thiol, that ends up being around 8.4. It's a terrible 4. If it turns into an OH, it's an amino acid known as serine, around 14.5, again around 15. So just knowing your relative pKs, you don't have to memorize these. You just know serine roughly 15, cysteine roughly around 10. Ends up they're both a little bit lower because of the conditions that created by those charged groups. But good idea to know your just random facts about pKs. Okay, how to make an alcohol? This was covered, and again, I want to just point or speak to the entire potential group of people doing this review. If you happen to be in a course I've taught or I'm teaching for organic chemistry, then we did this with SN1 and SN2, making something a better leaving group, or substituting for a leaving group and making alcohol. That's going to be the reactions we've learned. If you're doing this for some sort of test review course, such as a DAT, OAT, MCAT, anything like that, Straight memorization. You just have to know that you can make alcohols by substituting for the leaving group, or you can substitute for an OH, and we'll talk about that one in the next slide. But this is an SN2 reaction because it's a primary carbon. OH comes in, low temperature. As the temperature would go up and up and up, we'd start competing with an E2 and potentially run the risk of getting an alkene. When it's on a tertiary, in this case, no longer be SN2, it's going to be an SN1. You're going to end up doing it through slightly acidic conditions. And again, has be at a reasonable temperature so you do not complicate it with the risk of elimination. Strong acid, note that it went on a Markovnikov or more substituted carbon of the double bond. If you have the risk of rearrangement, then it could move around, which could end up on more substituted carbon. We sometimes use oxymercuration and then deoxymercuration or the reduction of the mercury species to get it on the Markovnikov carbon of the double bond. But this one, rearrangement could only go to secondary, which would give the same product. So this is the oxymercuration of which we speak. So this one, this would become important if that was here, it would still go in the same spot. If I had, let's say, something like this, then for that reaction, because of the rearrangement, in the end, I would most likely find this to be my product, for instance. So it would protonate and then rearrange. So just fun fact is that you can get rearrangement if you do it this way. You prevent rearrangement by using oxymercuration and deoxymercuration or reduction of mercury. So we're coming to addition. Let me get rid of my add-ons here and just turn it back to the original. And then finally, pH3, peroxide. Peroxide should be your hint, anti-Markovnikov, that goes on the terminal end. Okay, so we can react with alkenes to make them, or we can undergo a substitution. I could have easily used Br or iodine as a leaving group, but I chose chlorine just did. Reactions of alcohols. I want to keep in mind the chirality here. So this is just quick review of a previous podcast. So I'm going to go relatively quickly, but I do want to at least point out that this compound is made in the following way. The tosyl chloride and so there's something on the end there. Basically, this O is going to substitute here, and there's no way it happens in one step. Or it's not SN2 like it has to go, add, this kicks in, kicks out the Cl, which we'll go into. But I'm going to show a scheme. So this happens first, this addition. This happens second. They do not happen simultaneously, but it does happen. And then you end up deprotonating the H when it's all said and done. So that's your third step. And in the end, you end up with, instead of an OH, you end up with this bulky group. But notice this chiral center, if it was S to begin with, will stay S because you have not changed the priorities. It's still the exact same groups that you had before. Okay, so just get rid of that picture and tell you that you end up with RO with a tosylate group instead of an H, and it retains its chirality. There's also one with, instead of a benzene ring, we have a methyl group, methyl chloride, we end up with RO mess. You can also convert the OH into a alkyl group. So hopefully, there we go. This is going a little bit slower. There we go. Finally. Okay, so SOCl2, they will attack the sulfur, but when it attacks the sulfur, it's going to kick out Cl, and the Cl is going to come in from behind. So as this attacks sulfur, Cl minus that it generates comes in from the backside, SN2. Because it's an SN2, the chirality inverts. SN2 reaction, so inversion. So you'll note this is now R instead of S. PBr3 does the exact same thing. O will attack the phosphorus, kick out a Br, which comes in from the backside. So this will only work with primary or secondary. This reaction will not work on tertiary because tertiaries do not get SN2. reactions. Okay. You can also add HCl and protonate it, make water. You can also add HCl, a strong acid, and zinc chloride and turn it into a Cl. That will work with a tertiary. And then HBr, same story. It will work with a tertiary. But keep in mind, SN1 means racemic mixture. So alcohols, you can make them better leaving groups so they can carry out these reactions, or you can also convert them over through some of these reactions. Okay, so far so good. Last but not least, for this grouping, our introduction to alcohol and alcohol reactions, nothing has been covered that isn't part of something you've seen before. I still want to just group it together and make sure we review it. And then want to bring something up, and that is OH groups in OChem are unreactive. Well, same story happens in biochemistry or biology, physiology, whatever you want to look at. This molecule is something that's known as a terpene. It's a 10-carbon species which has this repeated fragment twice, and that is a 4-carbon chain with a methyl, 4-carbon chain with a methyl. So not that that's important now, but for this to be reactive, OH is a terrible leaving group. Biologically speaking, it gets pyrophosphorylated. So phosphate, phosphorylated, just put a phospho on there, pyrophosphate. And if you know the word pyro, probably I'm assuming from pyromaniac, but just pyro meaning fire, something that creates fire is very exothermic, releases a lot of heat. Same thing here, just like we get with ADP and ATP, you have a very unstable phosphodiester bond, which when hydrolyzed releases a lot of heat. So when you put this leaving group on here, it makes this a leaving group, but it also makes it an energetic leaving group. So if you have an unfavorable reaction, you can hydrolyze it and get the energy out to help carry out that unfavorable reaction. So a lot of times pyrophosphates make good leaving groups and a built-in power supply to make reactions go. Bad leaving group turned into a good leaving group. And then we have, in this case, something again we'll cover in a future podcast, but this cyclohexane with an O in it means it's a cyclic ether, except we have all these OHs on it. It's actually a carbohydrate. This is a monosaccharide. And if you know anything about the structure of it, everything is equatorial except for here. So this is actually known as alpha D glucose because it's a ring called alpha D glucopyranose. Not relevant yet, but it will be. OH is a terrible leaving group, so we not only put a pyrophosphate on it, but we also add this group as well. So we have a really great leaving group that again can be powered. So we take a poor leaving group, make it a great leaving group. So the reason I want to emphasize this is a lot of times what we do in OChem ends up being just a good idea that we stole from nature. Nature turns bad leaving groups into good leaving groups. So what do we do in lab? We turn bad leaving groups into good leaving groups. Okay, so this covers the intro, which in some case is a review. Hopefully this went well, and I will see you at the next podcast. So thanks for joining. Bye.